Now we talk about direct limit. So this has been taken from 3F of Hatcher. So you can think of direct limit as this disjoint union, and then you modulo out certain equivalence relation. So what it means is that, say you have this sequence of groups and homomorphisms, and say there is some group far away here which is say GK, and the sequence keeps going on, and say there is an element G1 here. So by this sequence of homomorphisms, say it gets mapped to M. So how will it get mapped to M? You first apply this phi1, then you apply phi2, and so on. So you keep applying maps till you reach say phi k minus 1, and then you have reached M. So say this element is eventually equal to some element here. Then you identify these two elements. So you identify this with this, and that is true for all elements. So all the elements which will become equal because of homomorphism, you identify them. Now in Hatcher, this is the definition given of equivalence relation. So you have, this is direct limit, your disjoint union, and then you have a equivalence relation. So this equivalence relation is so here you say G1 comma G2 minus phi1 of G1, and so on. A better definition is given in Wikipedia, which actually focuses on this definition. So it is better to see definition in Wikipedia also. Now this will be more clear through example. So for example, we are going to construct this rational numbers using this direct limit. So in commutative algebra, when you define rational numbers, you say 2 by 3 is equal to 4 by 6 is equal to 12 by 18, and so on. What essentially this means is that you say 2 times 6 is equal to 4 times 3. Then this is equal, you say 4 times 18 is equal to 12 times 6. So you're kind of gluing these things here. Just like we were gluing this G1 and M together. So once you glue them, the representative element of such is 2 by 3. Then you also glue these, you get 2 by 3. And you keep on gluing such relationships. Now you can also write this 2 by 3 as 2 by 18 is equal to, so I'm taking this fraction and this fraction, so 2 by 18 is equal to 3 times 12. So you glue these together also. So we have glued say 1, this is glued, this is glued, this is glued, all of them are glued together, or they're equivalent to 2 by 3. So this is the information we are going to use now to construct direct limit. So we are just going to consider the simple thing, and then you can have infinitely many representations like this. So what you do is you write integers, and then you write multiplication map. So phi1 is multiplied by 1, here you multiply by 2, multiply by 3, multiply by 4, 5 and 6. So 2 times 6, so say 2 is here, so 2 times 6 ends up here, and 4 times 3, so 4 times 3 ends up here. So these two we set equal to each other. And similarly for other elements like this, you will have 2 times 18, 3 times 12. Now 2 times 18 will come somewhere really far here. You will have, you are multiplying by 18, so you will have 2 times 18. This will be equal to 3 times 12. So 3 times 12 will come somewhere here where you will have integers. It's multiplication by 12. And then you will identify this. You will identify these two. So all these identifications will produce just a single element, 2 by 3. And so you construct all rational numbers. So basically you have fractions by putting these equal to each other. So this is how you construct rational numbers using direct limit. Now instead of multiplying by 1, 2, 3, 4, you multiply by prime numbers, you get this z1 by p. Same principle. Now we want to visualize this direct limit. So we will talk about mapping telescope, but let us start with mapping cylinder. So you start with this map f going from x to y. So say you have this x here and this is y here, and then there is a map f which acts on x and takes it to y, and now I'm going to draw the image of f of x. So this is f of x. So the mapping cylinder is, you take x and then you times interval, this I is 0 to 1. So let us make the mapping cylinder out of it. So this end is 0 and this end is 1. Now what you do is you glue this piece to the image right here. So you identify these two. So that is x comma 1 is identified with f of x. So this side is x comma 1. This is identified with this point, which is f of small x. And once you do this, this is what you get. You have y here, and then you have x here, and its bottom part here is glued onto y. So this is what the mapping cylinder looks like. Now instead of a single map, you could have multiple maps like this, and from these multiple maps we will make a telescope. So let me draw the telescope, and this identification is clear once I draw the figure. So this is how the telescope would look like. So what we have is, so this is x0, and this will say lie in x1, yeah, some map here. So this was x0, this is x1, and then this x1, say its image other end, it gets mapped into say x2. For clarity, I'm just going to delete other side. So this thing, and then this goes into x3, and so on. So this looks like a telescope. So obviously the interval here is 0 to 1, and this one and this one are the same. This is 1 to 2, then you start from here 2 to 3, and then 3 to 4. So this is x0, x1, x2, and x3. So that is it. This is nothing but disjoint union modular relationship, where what you do is you identify the end point of here. So this, so the end point of this is I plus 1. So this is the end point. So if it is x0, so you have x0 comma 1. This you identify with the first point of this. So end point of this, that is this one, is identified with 1 here. So I plus 1 with I plus 1, and that is it. I mean, we're just inductively repeating it, and this you call as the mapping telescope. So this is the mapping telescope, and you denote it as T. Now if all these x's are cellular complexes, this is cellular complex, this is cellular complex, this is cellular complex, and so on, and these are cellular maps, that is CW complexes and maps between them, then there is a theorem in Hatcher, I think it's proposition 3.33, which says if you want to compute the homology of this telescope, this homology can only be computed by using this direct limit of each and every of these xi's. So now you see how beautiful it is. This telescope itself is made via these disjoint unions, and therefore you can use direct limit to compute the homology of the telescope.